So one of the ways that we can actually measure the viscoelastic response and when that occurs is via dynamic mechanical testing. So that will allow us to probe this viscoelastic behavior. So what we do is we actually, you have basically like the cylindrical sample holder. You put your sample in that cylinder and there's a little plunger, a little cylindrical plunger that's then in contact with your material underneath. And again, usually it's viscoelastic material, a gel, and you start to apply a sinusoidal load. So at a certain frequency. So you can do scans at different frequencies, temperatures, and frequency is related to rate as well. Now the material will have a strain response, but that strain response will have typically a phase lag to it. So the material experiences a sinusoidal stress and a resultant strain as well. And you could break that sinusoidal stress that the material feels into two parts. One that's in phase, the cosine delta, and one that's out of phase, the sine delta. So the in phase, the cosine term is Hookean. It's your elastic response. It's the in phase instant response. The out of phase is your lag, the viscous response. So you could break down, you could apply this load to material, and we could probe which is the elastic response, which is the viscous response by this in phase, out of phase component. And if you break down that expression, you could actually measure what's called the storage modulus, which is again, that cosine delta, your elastic response, your loss modulus, E double prime or G double prime, which is your viscous response, the sine delta, the out of phase function. So you can measure those different components. That's extremely powerful. You can also measure the loss tangent, which is basically a ratio of those two values. So either way, and you could write in terms of complex variables and other things. But the cool thing is when you could actually, you'll do this experiment and you'll measure those values for different frequencies. So you'll pick a frequency, measure, and then you can plot and actually observe essentially this either the loss tangent or the G prime, G double prime, E double prime. And so we would expect that the storage modulus should be high at high frequencies and short times. So if I pull really fast, low temperatures, high frequencies, that should be my last response. At very, very, basically, my rubbery state should be at high temperatures or very, very, very low frequencies, long times. So, if we look at this plot, we see G double prime dominates at very, very low frequencies. That crossover point we see here is our relaxation time or relaxation frequency. It's the transition from, at low frequencies, our viscous response, because again, whichever curve is higher dominates. So on the left side, G double prime dominates. On the right side, our elastic response, our basically storage modulus dominates there. So we can tell the behavior of these different materials. When it's viscous, at what frequencies is viscous, what times it's viscous, when is it elastic. You could also look at the loss modulus to look at secondary transitions. So secondary transitions in polymers correlate to basically motions. So you see these peaks when molecules are able to move around. Alphas are TG. You always do the TG at the highest temperature peak. This beta term would be the next highest level of cooperative motion of several segments, but not quite TG. Then it could be a rotation of a group, it could be wiggling, etc., etc., etc. One of the cool things is you could actually, if you look at a semi-crystalline polymer versus a less crystalline polymer, LDPE, HDPE for example, you can denote and actually find which of these peaks are related to or associated with motion of crystalline regions and non-crystalline regions. So HDPE is very crystalline material. It is, the peaks that they have in common, those are associated with, the crystalline regimes. But for low density polyethylene, which has lots of actually high density polyethylene has lots of branches, you can see that there's different peaks that are related to motion of the branches and not. So next time we're going to get into time temperature equivalence as well.